starting today what are called the Vesumino terms. You must have come across this. Okay? Let me give you examples. Okay? Okay. There is a so-called in one space and one time, one plus one space time. Here he comes. We were thinking, should we start without Nemani or should we not? Then eventually your students push me to start. They don't love you. In one, I want to tell, well, you just, today I will want to start on this Vesumino terms. Okay? So my plan is I will finish this, then I will go into study of multiply connected spaces and the theta vacua in QCD. Okay? That is, then we will decide, depending on interest of the audience, where to go. Okay? Theta vacuum in QCD is clearly very important, so I will do that. Okay? This is also quite important. So let me remind you where you have seen it. Okay? In 1 plus 1 spacetime, for example, you have this Vesumino Witten model. What is this? I think it called WZW. Here the field. Okay. So the field G. Okay. In this model is a map from, let's say, two-dimensional space-time into some Lie group. Okay. Some, say, let's say SUN. Of course, n is larger than 2. And the model, the Lagrangian, rather people write the action as, and it is some constant which I don't remember. Then you have d2x okay, times g trace of g inverse d mu g squared. This is no big deal, but now comes another term, something like a quantized some n, let me put it, is something like, let me put within quotes, n divided by 8 pi squared. But here you get a three-dimensional integral, okay, and this is epsilon mu nu lambda trace g inverse d mu g, g inverse d nu g, g inverse d lambda g, and this n is quantized. Okay, but this is three-dimensional integral. And what is this third dimension? What is third dimension doing? Because the field is living on space-time, which is 1 plus 1, and where did this third dimension come up? Okay. Then there is some statement in the, well, if you go back to see Wesson-Zumino's paper, you see where it is coming from originally. But if you look in Ed Witten's paper, he puts it down, and I suppose to simplify matters, he says space-time is boundary or something, and he leaves it there. Okay. So what is this thing here? And this coefficient is quantized. So, huh? If you go back to Wesson-Zumino, you will see where they got this term from. They were trying to represent non-abelian anomalies which appear in Q's for 3 plus 1 field theories. Okay. When you have chiral, you don't have left-right symmetry, for example. No? So there are non-abelian anomalies. It's called Bardeen anomaly. Bardeen was the one who first calculated it for the non-abelian case, and they were trying to find an effective action for the chiral model. I'll write it down. Okay, which will give those anomalies when you gauge it. So they can do calculations on decay rates. Okay. And you can see why they got into this extra dimension. They come into this and try to solve some equations. Okay. Some equations for the anomaly flow. Okay. So there you sort of understand it. Here it doesn't explain it. He certainly knows what is happening, but that's not the point. Okay. Then there is in 3+1, there is another example. Physically, this is much more important than that one. Okay.
This is a topological term.
Yeah, but I don't know what it means. Okay. If you write like this, what is it? What is this extra dimension? Okay. Yeah. So it becomes very mysterious. Okay. In 3+1, what happens is, in the chiral, when you have in the chiral model, I am not explaining what these are, but never mind, because I will go back to something very simple. So with NF flavors, by the way, this term here, I prefer to write this as integral trace of G inverse dg, wedge D inverse dg, wedge G inverse dg, as a different in terms of differential forms. So if you are like, you can think of it as a shorthand, okay? But it is better to write it. Otherwise, okay. So in NF flavors, where NF is number of flavors is larger than or equal to 3. So you have up, down, and strange quarks. Okay? And I am looking at the chiral model. The pseudoscalars, mesons, are described by a field U, okay, with values in the group SUNF. Okay. This is a NF cross NF matrix, and its unit SUNF. Okay. So there are NF square minus 1 degrees of freedom here, and they describe for you the pseudoscalar matrices which come because of the spontaneous symmetry breakdown of the chiral symmetry. Okay. But never mind. Okay. So there, here what happens is analogous second term. Above is again some quantized constant. There is some I also. This is okay. There is some here, some again some quantized constant, which I give you the actual numbers later. Some n is some integer. So in integer times some fixed nothing like a 1 over 8 pi squared. I think here it is n divided by 240 pi squared or something. Okay. Then it is multiplied by 5-dimensional integral, and then you find this. So there is an extra dimension. So you write the 5-dimensional trace, okay, U inverse d mu u. These are all fields now. U inverse d sigma u. Okay, and you are integrating on 5 dimensions. 5th dimension. What is this? Okay, this is in the paper of West and Zumino. This last term. Okay.
What have you written? U inverse, then U, then what?
X, same thing.
Oh, I see.
Same thing repeated 5 times.
Right.
So this whole thing is trace of U inverse du wedge U inverse du 5 times. So question is, what is this? Okay. Huh? Say again. This is like a volume and group SU. No. X. I am not unfollowing.
So you have two-dimensional boundary. I mean, it looks naive.
Boundary of what? Does it mean? I don't understand. Okay.
It has to be.
In the way Ed is manipulating things, he doesn't need these details, so he leaves it. Then if you look at this flood of papers which came after him, he was doing that one and this one he was doing for the he observed that this model can be exactly quantized if the coefficients are this model. The coefficients are properly tuned, and that gives exactly a representation of the Casimir algebra of some level. Okay. But he didn't need the details, so he just did it in 2 pages. Okay.
So throughout the time you don't need what x. But throughout the time you don't need the x in this integral and that integral to be related.
The extra dimension.
Yeah.
So at least if you look at this, at least most people, if you look at it, you don't know what's happening. Okay. What is this extra dimension? So I am going to explain it to you. Okay. What it means, I will explain. Okay. I hope. Okay. It is the same thing that we already encountered. I mean, it already happens when you try to discuss the magnetic monopole discussion. Is a simple prototype of where this happens. Okay. You can reformulate magnetic monopole theory using such things, okay, which is what I am going to do now. So you can see what it is. They are all related to certain U1 bundles which lie on top of the configuration space. Okay. That's what I want to show you. Okay. And you can show the existence of the U1 bundle, but the okay, I'll show you. So somewhat before this, okay, there is a paper by Zakaria et al. Ending with my name. But I should write here Mukunda. And there is also Sudarshan somewhere. George, I think the paper was written in my absence. Although I was wondering, I think he did it out of spite and said anti-order the names. So once they did it, because the first author Franco is my friend and Mukunda is my friend, I didn't do anything. It didn't matter. Okay. So I will follow that treatment. Okay. So it is the paper has some funny statements in terms of the title and also some, well, I don't remember. Okay. But anyway, this paper is reported, appeared, and it is reported in our old book, Gauge Series and Fiber Bundles. Okay. There is an old book, not the present one, not this one, much older than this. Okay. That was sometime in the early 80s or so. Okay. We were struggling with understanding magnetic monopoles. Then we found this, what I told you, trace sigma 3 G inverse DG. Then we also found this other activity. Okay. So I want to show you, to explain what this is. So first statement is, I want to tell you what is called the path space of a PQ of a configuration space. Q. This exists for every manifold, and it is somehow a universal construction for trivializing all topological properties. Okay. This is known in math. It is a, okay, let me show you what it is. That I am going to tell you is what enters the picture here. So what is this? So the construction is follows: given Q, pick a point, any point you like, P0 in Q, and fix it once and for all. Fix it, don't change it. Huh? So you pick a point Q0. In the configuration space. Now what I am going to consider is, let gamma p be a smooth curve or path from this fixed point Q0 to P. So I am drawing a curve like this. Let me use a notation here. Yeah, it's okay. So gamma p is a path. Okay, so I can write here. See, gamma is a path ending at this point. Okay, which so this is a path which I can write as a path x of sigma. Okay, where x of 0 is Q0 and x at 1 is P. Okay. Sigma runs from 0 to 1. The path is unparameterized. That is, the path is oriented, okay, from Q0 to P. There is an arrow goes from Q0 to P, and it is unparameterized. Okay. That is, and unparameterized. That is, we identify if two paths have, if you put two different coordinates on sigma going from 0 to 1, we say they are the same. Okay. So it is invariant and it changes the coordinates here. Okay. So every expression I write will have this property. Okay. Now this is the path space. What is the interesting property of path space? The path space, so the set of all such paths, okay, is a path space. It is huge. We will, I mean, nobody in the right mind will try to do physics directly with them, but we will see that as we keep going, it gets highly reduced. Okay. Why is it? Now, the main thing here is this the path space PQ. Okay.
But it's just a subset of the configurations.
Is it a subset of?
Configurations.
No, no. It's a path. It's like strings. Consider all strings ending anywhere starting from Q0 in the configuration space. All strings, all open strings, but one end is fixed. Okay, huge.
In fact, Patha,
Our friend here.
It has a loop space, starting and ending at the same point, all the loops.
Yeah, you can do. I'll tell you.
Yeah, it's
Oh, he was thinking like this. I don't know. He has been talking to me about it. But here the structure is that in these problems, this does come. Okay, I'll show you. But as a fiber bundle, as a principal fiber bundle, I'll show you why.
So if Q and P are the same points, then special.
Yeah, that's the loop.
Q and P are the same point.
It is subspace.
It's a loop.
That's the loop space.
Right.
All
Right.
Now, loop space is clearly a subspace of here, so their P is Q naught itself.
Let me see. PQ is a principle. I will show you how to use it purposefully in physics problems. It's a principal fiber bundle on Q. I will show you. What do I have to show you? I have to show you a projection map, and I have to show you a group which acts vertically. Okay. So the projection map pi is what? Evaluation at the end point.
Initial point.
Last point is the projects a path, let's say gamma p ending in p, right, to p.
So the space is Q itself.
Yeah, Q is a bundle on Q. Okay. So this is in Q. So it takes a path. Okay, ending at P, and it simply projects here. Doesn't care about the rest. What is a structure group? The structure group is a loop group based at Q0. Okay, is the loop group. Okay, loop group. Okay, let's say which acts based at Q0, acting by loops based at, this is important. So it takes this thing, okay, and attaches, this is Q0, and attaches a loop here. Okay, at the beginning point. So the rule is, I'll come back to this, I go down. So the new path is, so the new path, I first, this is the action of the loop on this, it just attaches a loop. So this is the new path, gamma prime p. So gamma prime p is obtained by concatenation. That is, you first the loop, okay, then the gamma p. Let me write loop at Q0, then the union gamma p. Okay. Okay. This forms a group. Okay. Identity is a point. I mean, this is now, every loop is different from every other loop. So identity will be not attaching anything, just identity is one point. attaching one point, there is a loop. I didn't say that loop cannot be a point. Okay, can end in suddenly just it won't move. Okay, like some of us after a heavy masala dosa or something, it won't move until the food digests. Right? It is not good to attach it here because because this, if you attach it, if you move it, this P, you will get a loop based at P. Then you need an isomorphism between this group and the moved group. And in general, when we really start working with it, this isomorphism won't exist. Okay? So if you attach it to the base, from where you start, you are safe. Now notice that given two paths, say gamma 1 P, gamma 2 P, okay. You can go from one to the other by attaching a loop here. How? What I do is, okay, let me call it C, okay, where I first go along gamma 1 P, then union, then I will go along gamma 2 P in the inverse direction. Okay, be the loop. Oh, let me I'll make a be the loop, okay, at Q0. So here I am taking this gamma P, gamma 1 P, okay, then I go back like this, gamma 2 P, okay, let me make a statement here, then okay, after some identifications, here I made a mistake. On this, on PQ, okay, C will map gamma 1 P to gamma 2 P. I am sorry that this cannot be done. Problem is the following: if I just attach this, I will get another loop, another path. Okay. See, I got this path. Then I want to that is the point. Okay. Okay. This should be like this. Gamma 1 inverse. Okay. Okay. So this one, the problem is the following. If I attach, okay, what is the identification? I got this gamma 1 P, right? And I attach this, where this is gamma 1 P inverse is path gamma 1 P along the reverse direction, along from P to Q. I will tell you what the problem is. It looks very plausible, because what I am doing is I want to go from here to gamma 2 P, right? So what do? Attach a loop, but I go like this. To this I am attaching a loop, okay. See, gamma 1 P, yeah, so I should write gamma 2 P What happened now? Yeah, should be like this, no? I should start here. We should start here. Okay. See.
From left to back.
Yeah,
And completing the loop and going back.
Huh?
just start at Q naught,
Ah.
go in the new path to P,
Yeah.
come back in the old path to Q naught.
Ah, that's what I have done here. Okay. But only thing is, you have to agree that if I go along a path and come back, that is not a new path.
The reparameterization
But the path is different. Whatever be the parameterization, the path is different, right? Technically, if I walk like this, when I walk like this, I am not parameterized and I walk back.
oriented path. So going
Yeah.
back is a different path.
Path, so it's a different, going like this and coming back like this. I didn't tell you it is no path. Okay. So that's why I said you make further identifications. Okay. I will straighten this part out later. Okay. Because as is, it is the fiber bundle part, this bundle part is perfectly okay. But how the structure group acts, I need to make more statements. I'll come back to that later. Okay. Okay. Now,
So you have to define that going and retracing your steps back is the trivial loop.
I have to say that they are the same. They are the same. Some condition of equivalence between paths have to be given. Okay. And the way you give will be in terms of this Vesuvino terms, this curvature terms. I mean, I'll tell you how it happens. Okay. And it is quite interesting, and you will find suddenly that the bundle reduces from this huge thing, okay, to some G bundle, some group. I mean, given by bundle is given by some group. Okay. It can be Lie group, it can be discrete groups, and the discrete groups in the most interesting thing that comes in this picture are non-abelian groups. Abelian groups, it leads to, in quantum field theory, to theta vacua. The non-abelian groups leads to spectacular results, like non-abelian monopose breaking color. Okay. You get obstructions to color. Okay. All kinds of things start happening, okay, which are still not properly understood. So,
The fundamental group, the sum of your loop is the homotopy.
yeah,
First homotopy.
the homotopy group is this. Take this base loops, okay, then define them by homotopy. That is, identify two curves which can be continuously deformed to each other. That gives you the pi 1 of the space. Okay. If you make that identification, then on the paths also, so you should identify two paths ending at the same point. Suppose you identify them. If the loop where I go like this and come back is homotopic to triviality, then what you get is a universal covering space. But so if you identify by some other things, suppose you decide to do something really mischievous and say that I will give you a Wilson line from here to here. Okay. I just give myself a parallel transport operator, which you may call as a Wilson line. Okay. For some non-abelian group. So you are given the Wilson. I have not given the connection. Actually, I am giving you this whole thing along the path. Then you look at the inverse one from going along this and take the inverse, and you say I will identify the things. If that thing is unity in the group, you will get a G bundle. Okay. Okay. The G bundle will then depend on the connection. Of course, it should, because the curvature depends on the connection. Okay. So the path space is what they call a universal space. Okay. You give me any fiber bundle, there is a canonical map from the path space to that bundle, to that space. Okay. Okay. Everything is coming from factoring, making identifications on the path space. Okay. So that is why it is so huge. Okay. Is what they call, these maths people call as universal. It is a universal bundle. Okay. Now, what I want to says the following.
Sorry, just to understand the claim is that any fiber bundle with base manifold Q can be
Yes.
thought of as a sub bundle
As if
as a special.
the precise statement is, I will straighten this path business. I didn't come prepared how to order that properly. So the statement is the following. Give me any configuration space Q, okay, and any any principal bundle Q hat. Okay, so there is a projection map pi here. Okay, and is a projection map pi here. A principal and the fibers at different points of Q are all the same. Then the statement is that this is coming by mapping from there to here. So this is a bundle on Q hat, okay, and by factoring appropriate relations here, putting, you get this. So you can get everything, every damn thing you can imagine from Q hat.
So you're saying some equivalence classes of PQ can be Q hat
Ah.
with an appropriate relation.
Yeah, and the typical relations are, as I told you, you simply say like this. Okay? Homotopy is one. Homotopy is coming from flat connections. So the typical relation universally can be written like this. Give you as a connection, okay, and identify two paths as the same, ending in the same point as the same. If the parallel transport operator using that connection along that loop is unity, is identity. Okay, so if A is flat, you get discrete bundles. If A is a connection from a magnetic monopole case, I will show you. Then you will get this all the U1 connection bundles I have talked about. But if you put non-abelian things, okay, then you get this twisted bundles on the twos here, which comes in the ad hoc monopole, non-abelian monopoles in gut monopoles. Okay, if you do something else, you will get something else. Okay, if you do this for instanton, you get the instanton bundles on S4, okay, and so forth. Okay, so this is completely universal. Okay, of course, because it is completely universal, it is also topologically totally trivial. Okay, that is why it is, that is to say, all homotopy groups, all homology groups, all cohomology groups, this PQ is what they call contractible. Okay, and hence has all interest, like has is let's say topologically trivial. It's like R3. Okay, you can you can smoothly draw the thing to a point. Take all paths from Q0, no, ending somewhere. Okay, you can move that each point along the curve where you entered it and go back. So it is like like radial. There is a radial coordinate for anything you write. You can radially contract it, okay, along the path. Okay, so it is totally trivial. So this is the reason why it is so powerful, and also why it is such a mess, because it is so huge that you have to do something to be able to handle it. So what do we do? Now consider our magnetic monopole field. Okay, I will call it Fij, okay, which was, remember it was G over, I will get the factors, minus G over minus G over 4 pi, right, epsilon ijk xj xk dot over r cube. I think that's correct. this is a very good example where this is correct. Now what I will do is, the whole problem with the monopole field is comes because this is a connection, this is a curvature, this is a magnetic field. Fij O is Bi. So Fij will be the dual of this. So let me get the indices right. What did I do? This is not right. This is not right. Fij is, there is no dot velocity, no? Minus g over 4 pi epsilon ijk xk over r cube. Sorry about that. It's just a electric field, magnetic field of a monopole. Okay. Now the F is perfectly well defined. Okay, if we work in, we will look at the differential operator, imagining that there is a boundary there, and see what boundary conditions to put, okay, to make the operator silver joint. That is another enterprise. Okay, so that's also highly non-trivial. But let me go with it. But okay, we cannot write an AI such that this is a problem, right? Fij of x diaj of x minus ij, right? Hence the problem. So a Lagrangian, writing a Lagrangian with interaction say E ai of the particle, okay, z zi dot cannot be done. Huh? Because this will have a string singularity. If you try solving this for A, it's a problem in Jackson that you cannot find A, okay? Because basically because the flux a B dot ds around a sphere around the origin is 4 pi, okay? So but this will give 0 if A existed. So you have to remove a point. On each sphere you have to remove a point, so you get a string. So can I write an action using F alone? This is the question that this group was asking, okay? We were asking, okay? But so what do I do is, but the claim is we can write an action okay, where the interaction is written on the path space of Q, which is R3 minus origin. Okay, so what do I do? Origin is not there. Okay, so imagine that the action depends on paths, okay, on time dependent paths gamma, let me write, which is, let me write some gamma of sigma and t, okay. T is time, gamma of 0t is some fixed point which we have chosen q0, gamma 1t is actual x of t of relative coordinate. I will show you what I am doing. So what I am doing is the following. There is this trajectory x of t. The kinetic energy term will depend on this x of t. Right? The kinetic energy term I am not doing. If you want, you can put it also, but you can also think of it as gamma of 1 and t. This is gamma of 1 and t. This is my initial time t0. This is my final time t1. Okay. Now what I am doing is picking a q0 and I am imagining that there is a path here, gamma sigma t1 t0, and another path gamma sigma of t1 here, ending here, and there are paths going like this all along. The end points of the paths is my actual trajectory. Okay. The end points of the, so I am going to write the Vesuvian term. So the extra dimension is coming from the path space, and this is a two surface. Okay. So this path and that path is, you can see from this picture that the paths span the, so my initial time is t0 and final time is t1. Okay. So the paths from t0 to t1 span a, sorry, yeah,
Sorry, could you just read what is in that parenthesis?
here
Bracket, the whole thing. Fij, gamma of
sigma t.
yes.
So Fij is evaluated at some point here. Then this is a two form, no? So d gamma I or d sigma,
D gamma I.
contracting here.
D gamma K is what I thought you were looking. You mean I?
I wrote Fij is a two form. So in the components, it's a pullback of the F. Okay.
Why is f path dependent? It should only be sigma comma t, right?
It is integrated now over it is integrated. Where is the extra? It's a path. I am dealing with the path space, no? It's a space of paths. This is a path. This is a path. This is a path, and so on. Okay. And the paths are spanning a. When I go around this, they are spanning an extra dimension coming from the fact that I have a path. This is where the extra dimension is coming. And t is a standard dimension. But I should not get equations of motion here. If I get, then I don't know what I am doing. Okay. Now, so that this is a, so we should not get, we should get equations of motion, okay, only for the endpoints, namely gamma of 1t, which is x of t. Yes? Otherwise this system is nonsense.
Basically Q0 could have been any.
Sorry?
Q0 could have been any point.
Q0, it should, yeah, Q0, yeah, not only that, I should not get equation for this line. Okay? I should not get equations that this is moving in some way, because that has no meaning. Okay? These are all fictitious things I have introduced. It won't describe the charge monopole system. Well, what happens is the following. Okay? But in varying this object gamma sigma t is an action principle. We don't vary data at initial and finite times. Right? When I write an action principle, I don't vary the initial time and final time. They're held fixed. In the Hamilton's principal function, for example, is so. We don't vary data. When I write the classical action from an initial point to a final point, we keep in classical mechanics, we keep the initial and final point fixed and vary the extremize it in between. So we don't vary these things. I equal to 0, 1. Okay. Delta in the interior by a small m prime, pull it up, okay, having opposite orientation, okay, up to E over 2. Yes, the original action was F on this boundary. The other one is F on a little bump here. So the difference is F one way and then the other way. So it is F on this closed to surface. But this is 0. Why? Because F is a closed to form. By Biag, there is no flux, okay, which is 0. But I can do one thing. Okay. I can do something very quick. Okay. Choose a connection, yeah, okay, which is well defined on delta. This is certainly possible. I will just put more souped up grand unified model, okay, which provide you with lots of monopoles. Okay. In fact, it is very difficult to avoid monopoles. So this is what I wanted to say. If you have questions, I'll be glad. So I think I can show that the path space, the Weis-Dumonnet term in all field theories has the same source, that you get basically because of there are two spheres in your configuration space which cannot be shrunk to a point.
Delta has a time integral, right? The delta which you are integrating.
Delta is time, it is a space here. Well, you can write these forms as in terms of pullbacks of forms living on the groups. Okay, I'll do it next time. It's a little. If I start now, I'll say it too fast. So I'll try to explain it and explain the connection of this formulation and the formulation I gave earlier. Okay? The earlier formulation is much more clean. If you try to quantize this canonically, it's a big mess. Really is very difficult because you have a huge number of constraints. All the stuff inside is constrained, right? All the stuff inside that, all the points along the sigma except that at the end point is a constraint. It is not there. Okay? So if you write canonical formulation, you'll get a huge number of constraints, okay? And it's a pain. And when you go into quantum field theory, it is even worse. Okay? So quantization of these models very often happens because you knew the result a priori. Okay? You had some other reason, okay? Like Cauchy-Moody algebras, and you're expecting, there is a, for Cauchy-Moody algebras, you know Cauchy-Moody algebras, no? You'll see that Presley and Siegel have written this, okay, action in their book by using some activity from Kirillov. So there is some way of doing. So you know that having known this, you come back, you can manipulate. But if you start from cold blood, you start from here, we tried, it's quite hard. Because there are so many things which have to go to zero as a constraint. Okay. But on the other hand, intuitively, if you are happy with functional integrals, this is good. Okay. Because it is very, for some purposes, it is easier to handle. So one has to be eclectic, use one or the other, depending on, one should be opportunistic. That's the correct statement. Okay. Fearlessly use one or the other without bothering if they are consistent. So, okay, I'll say more if you want. If you want more on this, I can, but it is very common. This stuff is very common. If you do chiral models,